Swayam Prabha. Digital India. Educated India.
Welcome back, friends, to another session of fluid mechanics and rate processes. We have been looking at the energy equation, and today we will continue with our discussion on energy equation, and we will try to simplify it for certain special situations. So, let me recollect for you the control volume approach. So, we had a situation where there is a control volume and we made a control volume which is shown here with the dashed lines. There is an inlet port and there is an outlet port, and for this control volume, when we assume that the flow is steady, it is incompressible, and that it is 1D at inlet and outlet, we are able to write the V square by 2 plus Gz plus P by rho. This at the outlet is actually given as V square by 2 plus Gz plus P by rho at the inlet, and then we have to add here minus the Ws and Wl. Ws, as you recall, is the shaft work, and the shaft work is given as the work done by the control volume, that is positive, divided by the mass flow rate through the control volume, and Wl is actually the loss, and this is primarily because of the viscous action, and it has two components in it. It has essentially due to the U, the delta U, which is the internal energy, and then of course also due to the viscous. So, the work done due to the viscous forces. So, all those have been clubbed into the Wl. So, this is where we were. Now, suppose we have a situation where at the inlet and the outlet the flow is not one dimensional. So, what if the flow at the inlet and outlet is not 1D? Then it will be difficult to apply this equation. So, then what we resort to is we are going to consider a stream tube. So, we consider a stream tube. So, let us track a stream tube here. So, it may go something like this. This is a stream tube. Now, please recall that there is no flow across the stream tube. A stream tube is made up of streamlines. So, if I take several streamlines and put them in the form of a stream tube, then essentially what I am saying is that whatever flow enters at one end would have to leave at the other end, because there is no leakage of flow across the stream tube. So, therefore, I could treat this itself as a control volume. So, this can be treated as a control volume, and I would like to just maybe draw a set of dotted lines, dashed lines, to show you that indeed we are going to treat this as a control volume. Now, I could further say that this is an infinitesimal area stream tube. So, instead of taking a thick stream tube, I consider a thin stream tube which has a very small area, maybe an area dA, a small area at the inlet and a small area at the outlet. All right. Because the area is small, I can now assume that the properties across this stream tube do not vary. Okay. So, therefore, even if in a macro sense at the exit port and at the inlet port my properties are changing across the port, at least for this infinitesimal tube I can say my properties are not changing across it, they are constant, simply because it is infinitesimal. So, flow properties are constant across the infinitesimal stream tube. And then I can actually apply the energy equation. Not in this form, this was when the flow was 1D at the inlet and outlet, but I can go back to the original energy equation which actually had the integral over the control surfaces, so on and so forth. I am going to make a few other assumptions. So, I am going to say that further assume the following. So, I will assume a steady flow as before. I will also assume that the flow is incompressible. I will assume that there is no shaft work, there are no losses, which implies that I am talking about a frictionless or an inviscid flow. Recall, if I consider the flow through the stream tube, now the whole thing becomes a control surface, the whole stream tube. And therefore, if there are viscous forces, they are going to do work along the stream tube, because for sure the flow is along the stream tube by definition, and there are shear stresses on the surface of the stream tube. So, certainly they will do some work, and that would turn out as a loss that would contribute to terms of this kind. But I am now assuming that the fluid is inviscid, it is a frictionless fluid, and therefore the shaft work goes away, the losses go away, and in the limiting case of the stream tube, being a streamline, so I take the control volume which is already very thin, it is a stream tube, and now I take the limiting case so that the stream tube actually reduces to a line. and then I would simply get this quantity at the exit is actually equal to this quantity at the inlet. So, this would imply that V square by 2 plus Gz plus P by rho at the outlet is equal to V square by 2 plus Gz plus P by rho at the inlet. This is known as the Bernoulli equation. So, the Bernoulli equation says that along a streamline in an inviscid flow, so along a streamline for a steady incompressible flow, inviscid flow which has no losses and which has no shaft work, I have the preservation of the mechanical energy. So, this implies mechanical energy preserved along a streamline. What are the components of mechanical energy? There is the kinetic energy, the potential energy, and then this term pressure here arises because of the flow work. Okay, as we realized in the last few classes that when a fluid moves through a control volume, it is being pushed in and pushed out, and that actually appears as this term as the flow work. So, Bernoulli equation is simply a conservation of the mechanical energy. Now, we have gone through a long process. Okay, we first wrote down the balance laws corresponding to mass conservation, then we talked about the momentum balance in terms of the force equation, and then we wrote down the energy equation, the total energy equation, and we did a lot of work, and finally with these assumptions we came up with the mechanical energy. I must point out that this equation can also be derived from the momentum equation. I am not doing that for you here, but it's you can write down the, so if you wanted to do that in 2 dimensions, you can write down the x momentum equation, you can write down the y momentum equation, and then by taking a combination of those for an inviscid flow without viscous, without the unsteady term, that means for a steady flow you should be able to derive this back. Okay, so this is therefore the simplified equation for the flow, an inviscid flow, which represents the mechanical energy balance. Okay. It is different from the regular balance that you are aware of. So, if I take a projectile and I hurl it and I talk about the mechanical energy balance, and if I neglect the air resistance and so on, then usually it is a balance between the kinetic energy and the potential energy. That is what you already know. The difference here in a fluid particle is that a fluid particle also has to do some work against the pressure that exists in a fluid. So, as the fluid particle, a fluid element here kind of moves along the stream tube, along the streamline, it has to do certain work against the pressure. So, there is a pressure acting on it upstream and downstream, and that appears as this term. Okay, so, this is the additional term that you would get in fluid mechanics, which you do not see in dynamics of projectiles without air resistance. Good. We can use the Bernoulli equation to study several devices, okay, ideal performance of several devices, and I am going to show you a couple of examples. Okay. This is a very important equation, and I am going to apply it to some some situations so that you get a feel for it. So, some exposure to flow measurement devices. The first one that I wish to present to you is a Venturi meter. The problem is the following. Imagine you have flow through a pipe, okay, and you are interested in finding out what is the flow rate through the pipe, the volume flow rate. Okay, so how do you estimate that? Okay, that's an engineering problem. So I could have a gas pipeline, I could have a water pipeline, and as an engineer you are interested in estimating the volume flow rate. So what we can imagine is that there is a certain pipeline with a flow rate, and I want to understand what's going on here. So I insert in it a device which is called the Venturi meter. So let me show you what a Venturi meter is. So first I will draw the center line of this pipe. Let's say the pipe has the area A1. Okay. A Venturi meter consists of a converging diverging device, something like this. This point of the minimum area is known as throat. This part is actually the converging part, and this part, as you can imagine, is the diverging part. Okay. So this pipe is already available to me, which is carrying the flow, and of course it continues here. So what I could do is that in between these two sections of the same pipe, I could insert this device which I am calling as the Venturi meter. It consists of a converging part, a diverging part, and the minimum area region is known as the throat. What I am going to do is make two taps in this, pressure taps. So let me make the pressure taps. So just to show you that actually this is a different pipe, let me okay. So the Venturi part is a different device compared to the pipes, and I have just inserted it between the pipe which is carrying the fluid. Okay, so I have put two tappings here, two small holes, and I can measure the pressure here. So let me call these as, this is the section 1, and this is I am going to call as the section 2. Here I am going to measure pressure P1, and here I am going to measure pressure P2. Further, I am going to call this as area A1 and this as area A2. Okay. You will notice the way I have drawn that the diverging part is longer than the converging part. And I want to say something about that. So first let us consider the Bernoulli equation. So there's flow that comes into this pipe, and then of course it contracts. When it contracts, because the flow is incompressible and it is steady, so the flow will accelerate. Again, accelerate not in an unsteady sense, but the flow is of course steady, but as it moves, a fluid particle moves from the constant area section towards the throat, it goes through a convective acceleration. So the speed of the flow is larger at section 2 compared to at section 1. And from the Bernoulli equation, you can imagine I do not have the gz term because they are at the same level, so I can ignore them. And if my velocity at section 2 is smaller, is larger compared to the velocity at section 1, the pressure would behave in an inverse manner. So velocity is large, pressure is small, velocity is small, pressure is large. Okay, so the pressure actually reduces. So I would get some kind of a partial suction at section 2 compared to 1. If I can measure these two pressures, then possibly I can relate them to the velocity, as we will see, and get some kind of a volume flow rate. What is happening here is I go from a high pressure to low pressure. So this part, the pressure is reducing and we call it a favorable pressure gradient. The flow is moving towards low pressure. Okay. On the other hand, my pressure recovers here. So I had low pressure here because it's a high speed moving fluid, and then in the divergent section the fluid again retains its old speed. Okay, it becomes slower and then the pressure increases. So therefore, let me write it for you. This part is in a favorable pressure gradient, that means the pressure is reducing. On the other hand, in the diverging part, I have adverse pressure gradient. In the sense that if I am a fluid particle, I seem to be working in a favorable pressure gradient. So the pressure is actually welcoming the reduction in pressure. On the other hand, if I am a fluid particle which is either traveling on this part of the diverging section or on this part, I am moving towards an increasing pressure, and that causes me to separate. So I could actually separate from this wall because it's a curved wall, and if the divergence angle is too much, then it can lead to losses. So I will explain this with a diagram in a few minutes from now. But that is the reason, because we do not want the flow to separate, so we have to make the diverging part a little bit longer than the converging part. So the reduction in the area can be a little bit more abrupt, but the increase in area has to be gradual. Okay? All right, so let's go further with this analysis.